Dear students, continuing with our lecture series on oxidation reactions, in this lecture we will discuss what are the different functional group transformations using chromium reagents. Chromium, as you know, is 21st most abundant element in Earth's crust, and its atomic number is 24. And there are three stable isotopes of chromium which are present naturally: chromium 52, chromium 53, and chromium 54. And out of these three, chromium 52 is the most abundant among these isotopes, and it has the electronic configuration 3d54s1, which is half filled configuration and is a very stable configuration. And most common oxidation states of chromium, they are +3 and +6. In terms of chromium oxidants, the important reactions which can be studied under oxidation reactions is applications of Jones reagent, which is when chromium anhydride is reacted in presence of sulfuric acid, then this type of reagent created is known as Jones reagent. Then second important chromium oxidant is Peridenium chlorochromate, which is popularly called as PCC, and this is also a very effective selective oxidant in terms of application in organic chemistry. Then is Sarets reagent. When chromic anhydride is reacted in presence of pyridine, then the reagent which oxidizes the different functional groups is known as Sarets reagent. Then Coulon's reagent. Coulon's reagent is similar to Sarets reagent. Only thing is that chromic anhydride in pyridine is used in dichloromethane as the solvent, and this is also very effective for functional group transformation in terms of oxidation for different types of organic compounds. Then last is Peridenium Dichromate. This is similar to Peridenium chlorochromate. Only difference is that in case of Peridenium chlorochromate, we use chromic anhydride, whereas here we use dichromate as the oxidant in case of different functional group transformations. Now we will discuss these reagents one by one. First is Jones reagent, and basically what happens is that when chromic anhydride is reacted with sulfuric acid, then chromic anhydride reacts with sulfuric acid to give us a chromic acid as the product, and this combination of these two compounds is called as Jones reagent, and this is mainly used for oxidation of alcohols to the respective carbonyl compound. And it has been found that this reagent is a very selective reagent which is very useful for the oxidation of alcohols which contain either carbon-carbon double bond or carbon-carbon triple bond, which is alpha to the hydroxyl group, or we can say allylic alcohols or benzylic alcohols. They can be oxidized using Jones reagent, and the reaction is carried out at low temperature of the order of 0 degree to 20 degree centigrade, and the corresponding carbonyl compounds, they are formed as product. For example, if we are having this type of allylic alcohol, then when this type of alcohol is reacted with Jones reagent at 0 degree centigrade, then we will get the corresponding alpha beta unsaturated aldehydes as the product. But if we raise the temperature to room temperature, then the further oxidation of this aldehyde to alpha beta unsaturated carboxylic acid will be formed as the product. So depending upon the temperature of the reaction, we can get different type of products. But the allylic alcohols, they are oxidized to the corresponding carbonyl compounds, and these carbonyl compounds may be aldehydes or carboxylic acids or ketones, depending upon that at what temperature the reaction is performed. Similarly, in this case, where the hydroxyl group is attached to the carbon alpha to carbon-carbon triple bond, when Jones reagent is reacted at room temperature, then the corresponding ketone is formed as the product. Another example is the synthesis of natural product jasmine. This alcohol, when reacted with Jones reagent at -5 degrees centigrade, then this allylic alcohol part is oxidized to alpha beta unsaturated ketone. And the basic mechanism of action for Jones reagent is that, as I have told you, that chromic anhydride reacts with sulfuric acid to gives us H2CrO4. That is, chromic acid is formed as an intermediate, and this chromic acid reacts with the alcohol to form this type of chromate ester with the removal of OH from chromic acid and H from the alcohol, and we will get this type of chromate ester. And then this chromate ester undergoes rearrangement like this, removal of this proton by this oxygen of the chromium reagent, and we will get the corresponding ketone, and chromium 4 is formed as the product. So this is how alcohols, they are oxidized to ketones as the product. Then next reagent is PCC, that is Peridenium chlorochromate. Uh, Peridenium chlorochromate is synthesized when we add chromic anhydride to 6 normal hydrochloric acid in presence of pyridine. So pyridine will react with CrO3 and HCl, and we will get this type of ionic structure which is called as pyridinium chlorochromate, that is PCC. And this reagent is very stable at room temperature, and this oxidizes primary and secondary alcohols to aldehydes and ketones. The advantage of this reagent is that primary alcohols, they are oxidized to aldehydes, and no further oxidation to carboxylic acids takes place. So that is why PCC is a very important oxidizing agent which can be used for selective oxidation of primary alcohols to aldehydes. And the disadvantage mainly for this reagent is that this cannot be used for acid sensitive groups, because those acid sensitive groups, they can be affected, and some side products, they may be formed. These are few examples. So this is a general reaction where a primary alcohol in presence of PCC and dichloromethane as solvent at room temperature is converted into an aldehyde. Similarly, this is an example of allylic alcohol, or we can say benzylic alcohol, where a conjugated double bond is present in addition to the aromatic ring. So this cinnamyl alcohol is oxidized to cinnamaldehyde in presence of PCC and dichloromethane at room temperature. So here again, the advantage of this reaction is that the exclusive formation of aldehyde as the product. No further oxidation of the aldehyde to the carboxylic group takes place. Similarly, in this natural alcohol, this is a primary alcohol. The PCC oxidizes this to the aldehyde group as the product. And the reaction is a selective reaction. You can see that this keto group is not further oxidized to the carboxylic acid. So this keto group is not affected by PCC. Some more examples of Peridenium chlorochromate, and in these allylic tertiary alcohols, they are converted into alpha beta unsaturated ketones. For example, if you see this molecule, this part is our allylic tertiary alcohol, and when this is reacted with PCC in presence of dichloromethane and alumina, then this uh, tertiary allylic alcohol is converted into alpha beta unsaturated ketone. We will discuss the mechanism in the subsequent slides, but here first we will discuss most of the example. And here in this case also, if you see, this is the tertiary allylic alcohol part of the molecule, and you can see in addition this molecule is having carbon carbon double bond also and epoxide ring also, and only oxidation of this allylic tertiary alcohol takes place to give us alpha beta unsaturated ketones as the product, and other function groups present in the molecule like epoxide and carbon carbon double bond, they are not affected by the oxidant. So this we can say is a very selective reagent which will oxidize only allylic tertiary alcohols to alpha beta unsaturated ketones, and epoxide group or carbon carbon double bond group, carbon carbon double bond will not be oxidized. Then in this molecule you can see over here, this is the allylic tertiary alcohol part of the molecule, and in addition this is having this is the allylic tertiary alcohol part, and this is an additional functional group, that is carbon carbon double bond, and the hetero cyclic ring, urine ring, is also present. And this oxidant PCC does not affect either this heterocyclic ring or this carbon carbon triple bond. Only allylic tertiary alcohol part of the molecule is oxidized to alpha beta unsaturated ketone. Similarly, another example, this one here also, this part is the allylic tertiary alcohol, and you can see over here this is having benzoate group also and ester group also, and these groups, they are not affected by the oxidant, that is PCC. Only tertiary allyl alcohol is oxidized to alpha beta unsaturated ketone. So these, all these four examples, they show that PCC is a very selective reagent which affects only allylic tertiary alcohols, and all other functional groups, they are not affected by the oxidant. Now, as far as mechanism of this reaction is concerned, that there are two different mechanisms which can be followed depending upon that which type of reagent we are using. Whether the reagent is an acidic reagent or this is under neutral condition we are using. For example, Jones reagent, which you know is a chromic acid intermediate which is formed, and Peridenium chlorochromate. All these two reagents, they are acidic reagents, and whereas Peridenium Dichromate, which is a neutral reagent, it will follow a concerted pathway, whereas the reagents under acidic conditions, they will use the stepwise mechanism. So basically, if we take the case of tertiary allylic alcohols, When this is reacted with any chromium reagent like Jones reagent or Peridenium chlorochromate or Peridenium dichromate, they will first form this type of allylic chromate ester. And then this allylic chromate ester, if the conditions are acidic conditions, this will follow path A, that is stepwise mechanism will be followed under acidic condition, and the reagents is Jones reagent and Peridenium chlorochrome. So in this case, this will leave as negative part, and a carbocation will be formed, or allylic carbocation will be formed like this. And this allylic carbocation with the attack of hydroxyl group will be converted into alpha beta unsaturated ketone. Then if the conditions they are neutral conditions, then a concerted pathway will be there for this transformation. So this allylic chromate ester can be written like this also. So this will undergo this type of reorientation, and the chromate ester will change into another type of allylic chromate ester. And this allylic chromate ester then will undergo oxidation like this. This negative charge, that is anionic oxygen, will withdraw this proton from here, and a carbon oxygen double bond will be formed at this place to get it converted into alpha beta unsaturated ketone. So this is how different types of allylic alcohols, they can be converted into alpha beta unsaturated ketones either under acidic conditions or under neutral conditions. The next is Sarets oxidation. As I have told you, chromic anhydride in pyridine is called as Sarets reagent, and a mixture of these two is used to oxidize primary and secondary alcohols to aldehydes and ketones respectively. And here also acid sensitive groups and other oxidizable groups, they remain unaffected, and that is why this is again an example of selective oxidant. You can see over here, this is a tertiary alcohol. This is tertiary allylic alcohol, but with Sarets reagent, you can see that only this secondary alcohol, allylic alcohol, is oxidized to alpha beta unsaturated ketone, and this tertiary alcohol is not affected. So you can see that here the reaction is different from Jones reagent or PCC. In case of PCC and Jones reagent, we have seen that they selectively oxidize tertiary allylic alcohols, whereas this reagent is oxidizing tertiary secondary allylic alcohols into alpha beta unsaturated ketones, and tertiary alcohol is not. And other groups like tertiary butyl dimethyl silyl ether group is also not affected. Carbon-carbon double bonds which are isolated, they are also not oxidized to any other functional. So in that way, Sarets reagent is also a selective reagent which will only oxidize the secondary alcohol moieties which are adjacent to the carbon-carbon. Then next is Coulon's reagent. Coulon's reagent is different from Sarets reagent in only one way, that this is a 1,2 mixture of chromic anhydride and pyridine using dichloromethane as the solvent. In Sarets reagent, we are not using any solvent like dichloromethane. So this Coulon's reagent also oxidizes primary and secondary alcohols to aldehydes and ketones. So this is the structure of Coulon's reagent. One molecule of chromic anhydride reacts with two molecules of uh, pyridine to give us a 1:2 mixture of the reagent. So primary alcohol is oxidized to aldehyde. Here also primary alcohol is oxidized to aldehyde, and other groups like epoxide or ester group present in the molecule, they are not. So again, Poland's reagent is also selective in oxidation of primary alcoholic group to the aldehyde. Similarly, in this case, this is a secondary alcohol. This is oxidized to a ketone, and other groups present, ether group, for example, they are not affected, or side chain present on the ring is also not oxidized. Then is Peridenium Dichromate. Peridenium Dichromate, which is formed from the reaction of sodium or potassium dichromate with pyridine, and this oxidizes alcohols under neutral conditions without affecting other functions. That means this reagent is also a selective reagent which will selectively oxidize primary alcohols to aldehydes, whereas allylic alcohols, they are oxidized to alpha beta unsaturated carbonyl compounds, either aldehydes or ketones. For example, say this is an allylic alcohol. This is oxidized to alpha beta unsaturated aldehyde as the product. This allylic alcohol, where we are having a tertiary alcohol also, and carbon-carbon triple bond also. And these carbon-carbon triple bond and tertiary hydroxyl groups, they are not affected by PDC. Only the allylic alcohols, they are oxidized to the alpha beta unsaturated ketone as the. Similarly, this primary alcohol is oxidized to aldehydic functional group by PDC in dichloromethane in presence of molecular sieves. And here also the ester group is also present in the substrate, which is not affected by the oxidant. So again, this is an example of selective oxidation in presence of other functional groups like esters. Some more examples of PDC. This is again a allylic alcohol. This is oxidized to alpha beta unsaturated ketone as the form. Here also allylic alcohol oxidized to alpha beta unsaturated ketones, and mechanism we have already discussed, because PDC, this works under neutral conditions, and in neutral conditions first this allylic alcohol part will be oxidized to allylic chromate ester, and that allylic chromate ester will be converted into another allylic chromate ester, which on oxidation will give us alpha beta unsaturated ketones as the product. And in this natural product, you can see there are many types of functional groups present, and PDC is so selective that out of the various hydroxyl groups or ester groups or epoxide groups, it only oxidizes selectively this hydroxyl group, which is present at the top of this, and this is oxidized to keto group. And these hydroxyl groups, they are probably not oxidized because they are sterically hindered because of the presence of methyl group over here, and here we are having a ring, and here we are having additional functional groups present, and because of these hydroxyl groups, they become sterically hindered, and that is why they are not oxidized. Only this hydroxyl group is oxidized, and this group is also not affecting this ester function. The next is oxidation of alkenes. Chromium reagents, they are used for oxidation of alkenes to alpha beta unsaturated carbonyl compounds, and even epoxidation of alkenes can also take place depending upon the type of reagent which is used for these types of transformation. For example, if we react this substrate having carbon carbon double bond with sodium dichromate in acetic anhydride and acetic acid, then this will be converted into alpha beta unsaturated ketone by oxidation with sodium dichromate. Similarly, in this steroid, which is having carbon-carbon double bond also, ester group also, and keto group also. This ester group and keto group, they are not affected by the sodium dichromate oxidant. Only carbon-carbon double bond is oxidized to alpha beta unsaturated ketone as the product. So again, this is a selective reagent for oxidation of alkenes to alpha beta unsaturated carbon dioxide. Similarly, chromic anhydride in acetic anhydride, when this is used, the carbon-carbon double bond is oxidized to epoxides as the product. Then another chromium reagent which is very important is chromyl chloride. So chromyl chloride is used for oxidation of alkenes to carbonyl compounds, either aldehydes or ketones. They are formed when oxidation of carbon-carbon double bond with chromyl chloride in dichloromethane at low temperature is done. So in the first instance, this chromyl chloride will add across this carbon-carbon double bond to give this type of symmetrical chromate ester as the intermediate. And this on oxidation in presence of zinc and water will give us aldehydes as the product. Then similarly, aromatic side chains, they can be oxidized to different types of products when different chromium reagents they are used. For example, when paranitrotoluene is reacted with chromic anhydride in acetic anhydride as the solvent, this methyl group is first converted into diester of this type. Diestate group is replaced by two hydrogens from here, and then hydrolysis of this diestate ester will convert this into paranitrophenyldehyde as the product. So the selectiveness of this reagent is that the product formed is aldehyde, no further oxidation to the carboxylic acid takes place. Similarly, chromyl chloride also oxidizes the side chain of aromatic rings to aldehydes or ketones. So basically, chromyl chloride reacts with ortho, meta, or paraxylene to give the respective aldehydes in good yields. And selectivity, you can see over here that only one of the two methyl groups is oxidized to the carbonyl. So paraxylene will give us paratraldehyde, metaxylene will give us metatraldehyde, orthoxylene will give us orthotraldehyde as the product. Then dichromates, when they are reacted with aromatic compounds, the side chains they are oxidized to the carboxylic acid. No aldehyde or ketone is formed in these reactions. So, for example, paraxylene will give us 1,4-dicarboxylic acid benzene as the product, whereas paranitrotoluene will give us paranitrobenzoic acid as the product when these are oxidized with sodium dichromate in acidic medium. Then chromium based reagents, they can also oxidize the cyclic hydrocarbons partially to quinones. For example, 2-methyl naphthalene is oxidized to manadione when this is reacted with chromic anhydride in acetic acid as the solvent. Similarly, anthracene can be oxidized to anthraquinone under similar conditions. Then we can also oxidize the carbon-carbon double bond to chiral compounds when we use chiral chromium complexes as the catalyst. For example, if chiral chromium 6 silane complex, this type of catalyst where this L is triphenyl phosphine oxide, this is used as a catalyst, and then the carbon-carbon double bond is oxidized to epoxide in a enantiomeric product formation. So these are the various references which have been used for preparing this lecture. Thank you very much.